I wanted to walk through Activity 3, which we're not actually going to do in class due to the Labor Day weekend. And the first question of Activity 3 deals with the Census Data Set, which we'll actually see quite a few times in this class. So the government has to conduct the census every 10 years, and by law, everyone actually has to fill out the form and mail it back. But not everyone responds. And so what the government would like to do is to come up with a model that kind of predicts what fraction of people will not respond in a particular block so that it can more intelligently allocate workers. So the data frame in question is called census, and it comes with reg class. So the first thing we always want to do when opening up our studio and doing an analysis for this class is to load it up with library reg class. And in this case, we're going to load up the data set and then do some analysis on the associations. So I'm going to run just the data census here. I'm actually going to lump that in with the very first part of the code for question A here. And so what are the columns telling us? Well, response rate are the fraction of households in the census block that actually did mail back their surveys. And we have a bunch of other characteristics of the census blocks here. So if you'd like to know more details about what these columns mean, you can always do a question mark and the name of the command or the name of a data set that's built into R or a package. And you can read about exactly what all of these columns are referring to. Okay, so what we want to do is we want to be predicting response rate. We'd like to know what factors seem to matter when determining the response rate for each census block here. So our first question is to pick out 5 variables that are the most strongly correlated with response rate. All right, so we can analyze all the associations, all the correlations directly by using the command allCorrelations or by using the command core.matrix. I'm going to use the command core.matrix first. What I'm going to do is I'm going to pass it the name of the data frame, and I'm going to press run. Now what this does is it creates what's known as the correlation matrix and basically reports each pairwise correlation between every set of variables in the data set. We just reran it here. Now there's so many different variables in the data set, this correlation matrix is extremely overwhelming. But if I was interested in looking to see what was highly correlated with response rate, I could actually look down the numbers of this column, the column corresponding to response rate. So it looks like the area of the census block has a correlation of 0.124. The fraction of households that lived in urban areas in that census block had a correlation with minus 0.132. So in theory, I could use this matrix, kind of go all the way down these rows to pick out the variables that had the strongest correlation, but that's kind of relatively inefficient, not a good use of our time. So instead, what we're going to use is the command allCorrelations. So in allCorrelations, I gave it the name of the data frame that contains all my variables. And then I say, all right, in this case, I'm really only interested in what is correlated with response rate. So I'm going to add an argument, interest equals response rate. And if I run this, then what it will do is it'll print out a list of all the variables in the data set and their correlations with response rate. Now this is still kind of a pain in the butt to look through because this is a very long list of correlations, and so I can actually add in the additional argument sorted equals, and then in double quotes I can put in strength to sort those correlations by strength. Now one thing to remember about correlations is that the farther from 0, the stronger the relationship. So a correlation that is close to -1 is a strong relationship, a strong correlation, and a correlation that's close to +1 are also strong relationships here. So basically the ones at the very top of this list and the bottom of the list represent our strongest correlations, and in this case we want to pick out the 5 that are most strongly correlated. So the sign of the correlation doesn't matter, just the farther away from 0, that's what matters here. And so it looks like we have renting households, which has a correlation of -0.607. We have female head of households, which the correlation is 0.556. We have age 18 to 24 with that correlation of 0.522. I'm going to skip down to the bottom of that list now. And then we have homeowner, HH, with a correlation of 645. We have whites with a correlation of 0.561. And we have married, HH, with a correlation of 0.554. So, okay, the farther from 0, the stronger the relationship. So it looks like the weakest of the 6, since I only want 5, is this variable right here. So I'm going to delete this one. And so now I've picked out those 5 variables that have the strongest correlations with response rate. It looks like these 5 variables seem to matter the most when predicting the response rate for the census block. Okay, so part B asks us to take the variable that's the most correlated with response rate, so the most positive or the most negative correlation, and in this case it is homeowner household because the correlation is farthest from 0. And what we're going to do is we're going to run associate, calculate r squared, the square of the correlation, and interpret its value. So the associate command works like it has been working. Basically the syntax is associate y twiddle x, data equals name of the data frame, and I just need to replace x and y with how they're assigned. So in this case I'm trying to predict the response rate, so my x variable, what I used to make that prediction, is homeowner household, and I'm trying to predict response rate, so I'm just going to copy and paste. And the data frame that I'm looking in is called census, and let's run it. Oops, so I probably have some sort of typo going on, and I don't see it, so you're not the only ones that run into this sort of issue. Home, extra W, there we go. So, there we go. We have about 3,500 different census blocks. Here's our scatter plot showing the relationship between the response rate and homeowner households. So basically we see a positive relationship because the trajectory is heading up and to the right. We see that it's well described by a straight line, so it's linear, and it's moderately strong. There's a bunch of vertical scatter here, but I can definitely see some sort of pattern. I can see a trend. Okay, so what is the numerical measure for the strength of this relationship? What is Pearson's correlation? Well, we look in the output of associate, and it looks like the value is 0.645. So to get r squared, all I got to do is square that, so 0.645 quantity squared, and that evaluates to 41.6. So the way I interpret this is I can convert that into a percentage, and I say 41% of the variation in y values being response rate, so in response rates, can be attributed to differences in homeowner households. So in general, I interpret r squared as r squared percent of the variation in y can be attributed to differences in x. So I see the response rate being really quite variable, and once I know the homeowner household, that can reduces the variability in y, the spread in y, by 41.6%. Another more informal way of interpreting it is saying that knowing x, in this case homeowner HH, gets you about 41.6% of the way there to knowing y, which is response rate. So that informal way of interpreting r squared is saying knowing x gets you about r squared of the way there to knowing y. So that's what that value is meaning. So pretty interesting. Once we know the fraction of households in a census block that are occupied by homeowners, we get about 40% of the way there to knowing the fraction of people in that census block that are going to respond to the census. And that's pretty big. That's one single predictor actually tells us a lot about the response rate. All right, part C asks us to make a scatter plot with y being log median household value and x being median household income city. So the plot command in general is just plot y twiddle x. We say what data frame that it's equal to or inside. And in this case, I say that y is log median house value, x is median HH income city. So I'll replace those two. And the data frame I'm looking in is census here. So we're basically using the median household income for the city in which that census block is located as a predictor of the median house value of that census block. So if I click Run, that brings up the scatter plot here. And so we see that it's a positive relationship. Larger values of x are typically found with larger values of y. The trajectory is heading up and to the right. And what we're being asked is to describe the direction and form of the stream of points. Does the stream have unusual features? Which measure of Pearson versus Spearman should be used to measure the strength of the association and why? So we just addressed this. It's a positive relationship, since the trajectory is heading up and to the right. And it looks fairly linear. It's a little bit difficult to tell because there's so many different points. Maybe there's a little bit of curvature here. It's kind of difficult to say. I'm going to say essentially linear here. There's a hint of curvature. And does it have any unusual features? Well, there's maybe these two guys are outliers here with weird combinations of home values and incomes for the city. So we can say there are some mild outliers. So not too far away from the rest of the stream. They're kind of mildly different from the rest of the data points here. So, all right, which measure? If we wanted to describe how strong this relationship was, we have two choices, either Pearson's correlation or Spearman's rank correlation. And the way that we decide between the two is that we use Pearson's as long as the shape of the data cloud is very well described by an ellipse. If we see curvature, if we see heteroskedasticity, where the vertical spread is larger for some values of x than other values, which we do kind of see here, we see that the house values are spread out quite a bit at low values of x, whereas there doesn't seem to be as big of a spread up here. So I can actually add that, and heteroskedasticity, unequal vertical spread. So because this shape does not really, look like an ellipse, I'm going to say that we should be using Spearman's rank correlation instead of Pearson's correlation, since Pearson's correlation is only valid for point clouds that look like ellipses here. So Spearman's rank correlation is the appropriate measure since the point cloud does not look like an ellipse. So there's potential curvature and clear unequal vertical spread. That vertical spread is a lot bigger on the left than it is on the right here. All right, so question 2 now asks us to load up the Survey 10 data frame that's built into Reg class. So I will do library. I'll do data Survey 10, run it to make that data frame available. So there it is. And so the context of this is in terms of thinking about student profiles. Maybe we can group different groups of students together to make a common kind of set of characteristics. Maybe they're all interested in sports. Maybe they're all interested in gaming. Making profiles of students or customers in general are really useful things for marketers to do so that they can do focused advertising. So they only give the ads to people who they think are going to be interested in it. So we might be interested in seeing, well, what variables seem to be correlated with one another? What values tend to be seen as pairs? So we can run core matrix, like what we had done previously, to get an idea of all the pairwise correlations. In this case, I'm asking to only do the correlation matrix of the first 7 columns of the data frame. So if you remember way back, if I wanted to refer to a specific set of columns, I put a pair of square brackets after the name of the data frame. I leave the number in front of the comma blank because that refers to the rows that I want. In this case, I want all rows, so I can leave it blank. And in this case, I want the first 7. So I can get the first 7 by putting together the numbers 1 through 7 as a vector. Basically, the number separated by a comma and then wrapped inside of a C parenthesis. So this will extract the first, second, third, fourth, fifth, sixth, seventh columns of the Survey 10 data set. And so we're just looking at the correlations between there. All right, so here's our correlation matrix. And what we want to do is we want to figure out, all right, well, which of these correlations seem to be the strongest? And just by looking at the correlation matrix, it's hard to tell because, we might see something that looks to be fairly strong, like this 0.871, but it's easy to miss values that might be a little bit bigger or even larger on the negative side of things. So a better way is to actually run all correlations, and in this case, we're not going to restrict ourselves to the first 7 columns. We can run all correlations on the entirety of the data frame by typing in the name of the data frame, and we're going to add the argument sort equals strength so that this list is sorted from the most negative up at the top to most positive at the bottom here. So we know a correlation is strong when it's very negative, close to 1, or very positive, close to 1. So it looks like the most negative correlation is between desired weight and number of body piercings with a correlation of minus 0.588. The most positive correlation is weight with desired weight with a correlation of 0.87. So that's farther away from 0 than the piercings and desired weight that we saw up at the top. So we would say that, if I can spell correctly, weight and desired weight have the strongest positive correlation. Gosh, my spelling is off today. Desired weight and the number of piercings has the strongest negative correlation. And I'm asked for what the strongest overall relationship is. Well, whichever correlation was the farthest from 0 is the strongest. So the correlation between weight and desired weight is the strongest one. So they have the strongest overall correlation since it is farthest from 0. And then finally, I'm asked which quantity has the strongest correlation with GPA. Well, we can rerun all correlations, just isolating our variable of interest. So I can say interest equals, and then the name of the column that corresponds to GPA. So I'm going to type in GPA here. We're going to run this, and it looks like the most negatively correlated variable is weight, with a correlation of minus 0.2. The most positively correlated variable is percent more intelligent than, with a correlation of 0.15. So actually the most correlated is with weight for whatever reason. So it looks like weight has the strongest correlation with GPA with an R value, a correlation of minus 0.21. So all of this analysis was done just by looking at Pearson's correlation, and that's assuming that the stream of points in the scatter plots are well described by an ellipse. And I didn't make any visualizations to double check that, so it's kind of a bad practice on my part. I can go back now and just look to see, okay, if I tried to use someone's weight to predict their GPA, what does that scatter plot look like? Let's make sure that what we're doing makes sense. And, overall, yeah, this looks to be pretty well described by an ellipse. We do have a few outliers here at GPAs of 0, which actually corresponded to freshmen. So in case we were worried about this kind of contaminating our results, because we know that outliers can really mess up the value of the correlation, we could actually rerun this. Instead of outputting Pearson's correlation, we could say type equals Spearman to get Spearman's rank correlation. It'll give a bunch of warnings because there's ties in the ranks and it has difficulty with that, but that's of no concern to us. But the answers hasn't changed too much. In fact, instead of the most negatively correlated being weight, it's actually desired weight instead. It's slightly edging it out here. So the results actually don't change all that much. This point cloud looks roughly elliptical, maybe a few outliers that are a bit troublesome. But really either of these measures give a pretty good idea of what is the most correlated. Pearson's correlation says the top 2 are weight and desired weight. Pearson's rank correlation say the same thing, just the order is switched slightly. So we have a pretty good idea that, for whatever reason, someone's weight or their desired weight seems to be, of the variables collected, the most strongly associated with college GPA. All right, so we've worked through activity 3. I'm going to go ahead and compile that and upload those solutions.